There are different packet types. So there is something called message type that is separate to. There is not packet type. Packet type is different. Message type is different. Here we have 5 different packet types. Hello packet, database description packet, LSR links to request packet, LSU links to update packet, LSAC links to acknowledgement. This is not LSA, this is LSAC. LSA is update, but that update we see here, DBD, database description, DBD. So we got hello, database description, LSR, LSU, LSAC. 5 types of packets. These numbers, they are not serial number. They are reserved to identify these packet types. For example, if you see type as 3, then it means it's LSR. When we capture a packet, and we will be able to know what type of packet it is by seeing this number. This is how the header looks like. See, the protocol field on the IP header will only have this information. It will say IP89. IP89 is the ID given to identify this protocol. So in layer 3 header, when you have IP89, layer 3 will have a new layer right at the edge of layer 3. A new layer will begin. It's also part of layer 3 called OSPF. I repeat. All the necessary information about OSPF like this need to be carried in every OSPF packet. Where it is carried? Carried in layer 3. Kind of extension. Depending on what protocol. See, right now we have OSPF, so you will have OSPF header attached to layer 3. If it is EIGRP header will be attached. So what I'm trying to say, this is not a separate OSI layer. This new fields, this header is a part of layer 3. It's an extension to layer 3. So this is how the OSPF header will look like. It has got all these fields like version number, IP version. Oh, sorry, not IP version. This is OSPF version number. It's not IP version. IP version is 4, no? But the OSPF version is 2. I repeat. IPv4, it means for version 4. IPv4 OSPF is version 2. You will see that number here. 2 means version 2. IPv6 version of OSPF is version 3. So if you'll see 3 here, then it is IPv6 version of OSPF. So version number you will see followed by the type. type here means the one which we just learned in the previous page. Can anyone say what is type 3 means? If I have 3 here, what does it mean? What packet it is? You may be in mute, you need to unmute if you're saying. Type 3, what packet it is? What type of packet? You just saw in the previous page. Are you there? I can't hear you.
Yes, sir.
Okay, what is the type 3 means? Okay, type 1 is hello. Type 2 is DB. Type 3 is LSR. LSR. So the type is carried there. That number 3 means it's LSR packet. Link state request packet. See previous page. LSR. Link state request. Type 3 means. Packet length, it shows the size of this OSPF packet. Router ID. Each router will pick a 32-bit address from the router's interface as an ID. That will be shown here. More about router ID we'll discuss in a few minutes. Area ID, area to which the router belong to, the interface belong to. Checksum value for integrity. If anyone takes OSPF packet and alters it, the checksum value will break. So the receiving router will understand that this has been modified, we should not accept, and we will ignore it. Modified packets will not be accepted. Authentication type, authentication password, and then the data, the OSPF data. Because it's a OSPF link state request, that request will be carried here in this data field. Right, I'm going to show you this in the command line. See, I have two routers started, and when I go to router 1's console and say debug IP OSPF packets. Okay, I don't want anything more. This is enough. Listen, this is that header that we saw there. This is what you are seeing here. You see, version. This router is receiving a packet, and it's a OSPF packet. In this time, June 9th, this is the time, and this is OSPF packet received. Version 2, this field. Type 1. What is type 1?
Is it hello packet, sir?
Hello packet. Length 48. That's the size of the packet. Router ID, I told you, router will pick one address as its identification for the whole OSPF. That router ID can also be manually configured by us. When we don't configure router ID manually, OSPF will go and pick one of the address on the interface as the router ID, preferably the loopback interface address. If in case you don't have loopback interface, among the physical interface IP address, it will pick the highest IP address. Highest OSPF is highest. It picks the highest IP address. Area ID. This means area 0. Checksum value. And then authentication is type 0. Means no authentication. So no password. You see? All these fields you see here. So there in the command line. I can also show these things in a packet capture using Wireshark. Let's go. See, this is OSPF. How do I know 224.0.0.5 is the multicast address OSPF uses? Kindly note, the multicast address used by OSPF is 224.0.0.5. And it's a OSPF packet. If you go to the layer 3 header, and there you see the protocol field says protocol is OSPF IGP 89. IGP 89. And if you down go there and open this OSPF, this is OSPF header. OSPF header, you see, these are the things that we saw there. Version 2, isn't it? Version 2. It's a hello packet, type 1. Length 40. It's the same information that you saw there. There's no big difference. You see? This is received on router 1, whereas this one is sent from router 1. See, source is router 1. So let me show you the received one. Router 2 is sending. Now if you compare this and see, it will be same. Version 2, see version 2. Type 1, length, sender, source, router ID is 1012.02. Area ID is 0, which means coming from backbone. All that you see in the bracket, no, these are all suggestions given by Wireshark itself. These are all not actually, see the word backbone and all, you don't see here in this capture. Is it written anywhere backbone? No. These are all suggestions given by the tool Wireshark, which we are using for capturing the packet. And then the checksum value, you see C365 here and C365 here. The authentication is null authentication. Acknowledgement is 0. Yep. So likewise, every packet you can see. Now these are the things that we will see inside OSPF. A hello header. hello packet. Hello packet carries these information. Let me show you that here. See, it's the OSPF header I showed you, and it is the hello packet. It is type 1, no? See, type 1 hello packet. So when I open that hello packet header, what all you see? We see net mask. That net mask also should match. It's not listed here, but that should match in order to form neighbor. That's mandatory. This must match with the neighbor. Both sides the net mask should be same. Secondly, the timer also should match. If you see here, they mentioned here timer, the hello time and dead time interval. You see the star means must match with the neighbor. And then the timer, and then the destined DR router, BTR router, designated router, IP address, active neighbor. If NSSA is enabled, stub field, right? We don't have authentication enabled, so it's not showing authentication. It's not showing authentication, the password, because it is not enabled. We don't have any authentication enabled. If I enable, then you will see here. Let's not go into that now. So in a hello packet, these are things carried, in which parameters that's supposed to match in order to form neighbor are the hello packet time intervals, area ID, authentication password, flag, subnet. Subnet mask. Now, this was once, interview question, very famous. I don't know whether it is still there. They'll ask what are all the things in the OSPF hello packets that should match in order to form neighbor. Hello and dead interval, area ID, authentication, subnet, mask, subtypes. Now we are going to see the adjacency stages, adjacency states. There are 7 different adjacency states through which the OSPF needs to go through in order to form neighbor. 7 stages. For example, we have enabled OSPF on this router, not on this router. So what will happen to the OSPF adjacency? It will be in a down state. Down state. Because one side only you have enabled. Next. After we finish configuring OSPF on router B, the packet that goes from A will be accepted in B.
Sir,
Yes.
So by default, it will be in down state, right? Then only in its state.
Yeah, see, very first time it will be in down state.
Okay.
Until
No, I thought even if we enable OSPF in both the routers at the same point of time, I thought it will come directly to init state. It will be
no,
initially down state.
initially down state, and one of the routers should
Exchange the hello packet.
accept.
Okay.
That is the
So
time
till
it
the time
becomes
of
init
acceptance,
state.
it will be in down state only.
Correct. Yeah. So from down state it goes to init state when one router's hello is received by the other. Because that is the very first initialization packet. Very first initialization packet for forming adjacency. the very first initialization packet. So this one becomes init state, initialization state. This packet makes the router. Which router? Router B. Router B says I'm in an init state. Now in the init state, the hello packet is received with the neighbor list, meaning A will have a list of its own neighbor in a field of this hello packet that is sent from A. So B learns the neighbor list also. Not only B learn about A, B also learns about A's downstream neighbor, A's other side. And now when B send a hello, B will send the neighbor list in which A can find itself, because B has already learned about A. That makes A to say, right now I'm in a two-way state because I know him and he already know me. I can see myself in his neighbor list. And then it goes to Xstart state. Xstart state, not all router will go to Xstart state. If it is point to point, there will be two routers. If it is point to point, there will be only two routers, so they will go to Xstart state and then following state like exchange, loading, and full state. There is something called DR, designated router, backup designated router, BDR, and DR other in a multi-access environment, not point to point. Point to point is connecting through a WAN cable, serial wire. Multi-point is connecting through Ethernet via a switch. You got more than two routers. That is multi-point. So when we have more than two routers, there will be something called other routers, DR other routers. Those DR other routers will only form two-way relationship, meaning they will stop here itself. Downside, initial two-way state. That's all. They won't go further. So what is two-way state means? I know him. He already know me. That is two-way state, right? So they know each other, but they are not sharing anything here other than the hello packet. They don't share any LSR, LSU, DBD. No, they don't share type 3, 4, and they don't share type 2, type 3, type 4. Type 5 is an acknowledgement. Yeah, I can say even type 4 is not, 5 is not shared. I repeat, if two routers are in two-way state, they only share hello packets, type 1. No type 2, no type 3, 4, 5. Means they're not going to share any updates, DBDs, requests. But we will also see all the other routers forming full adjacency with DR, which means they are going to go through this other states like Xstart state, exchange state, loading to full state. What is Xstart state? So after two-way state comes Xstart state, what it is. As the word says, exchange start. Xstart means what? Exchange is going to start. Exchange of what? Exchange of type 2. OSPF packet type 2, DBD, exchange of DBD. Exchange of DBD is what called as type 2. Now, type 2 is shared if it is not DR other router. Type 2 is also shared if it is point to point. More about this is coming later. Now what I want to say here is in the start state, they don't really start the exchange. They just decide who will initiate the exchange. Who will initiate the exchange? Will left hand side router or the right hand side router? Who will initiate the exchange? That conclusion they need to come. The one with the bigger router ID will always initiate the exchange. You see here, this router, let's say router 1 and router 2, router 1 is trying to say, I'll start the exchange. But this guy whose router ID is bigger, this guy router 2 says, no, I will start the exchange. Because my router ID is big. Right? So they come to conclusion who will initiate the exchange. After which the exchange starts. Both exchanges, DBD, and then loading state. Loading state is when they exchange, they exchange only the DBD. What is the database of OSPF called as? What is the database of OSPF called as?
LSD.
LSDB, correct. It's called as LSDB, but instead of sending LSDB, it is sending only the summary of LSDB. It sends only the summary of LSDB, which is what we call it as DBD, database description, DBD. Summary of LSDB. So the summary of LSDB is shared between these two routers. They're not detailed. But summary will be most of the time more than enough. They will understand. Even though it's a summary, they will understand. The routers will understand. But there will be sometimes some queries need to be clarified. That queries will be sent during this loading state. For example, this router is saying, R1 is telling, I need a complete entry information about this network. The summary that you gave me is not clear. I need some more info. For that, this is what we called as LSR, link state request, asking for clarity, more info. For that, LSU will be sent. We call this as loading state. Loading. After loading state, both the routers are a full state, meaning they don't have any more query. They are fully synchronized. So it sends an acknowledgement saying, done. We are synchronized. There is nothing more. Thank you. Acknowledgement. We call that as full state. So whenever OSPF adjacency is formed, you can see those things, but not in the complete 7 stages. You can see loading to full, meaning it has gone from this stage to this stage is the final stage. If you really want to know all these 7 stages clearly through the command line, then you need to enable the debug. Debug IP OSPF adjacency. When you enable this, you will be able to see every single stage. Let me do that. Clear IP OSPF process. I'm restarting the OSPF process. So you will see. Look at this. That's all. I stop it. Now if you go and see from the top, because I cleared the OSPF, it went down and then it has come up. Look at this two-way state. The other side should have been init state. After two-way state, they go to extra state, like who will initiate. For that, an election is happening. And at last, router 2 says, I am DR. See, dot 2. Router 1 says, I am BDR. I am backup designated router. So, DR is the one who is going to initiate. Say, DR is ending the exchange, DBD. So, when it is sending DBD, it is not going to be detailed, it is a summary. Right. So, that is what called as exchange state. Sharing DBD. And then, see, link state update, LSU, LSR. This is what called as loading state. They send LSR and LSU asking for some details. That's what loading state is. At last, when there is no more to query, no more LSRs, it reaches full state. Any question?
No, sir.
Now, as I said earlier, if it is a WAN link, you will have a link like this. This represents WAN link. There will be only 2 routers. You cannot have the third router. So there won't be a designated router and backup designated router election. There will not be. There won't be. But when we have Ethernet wires, at any point of time you may connect a switch in the middle and have many routers. This is 5.1, this is 5.3, and you will have 5.2 here, 5.4 here. When there are too many routers, router 4, router 1, if anyone sends an update, all will receive it, but what will happen if they also forward the update to others? Then that will become duplicate. Whenever there is a duplicate update, there will be a loop. To prevent loop, one router will be elected as a designated router, the router with the highest router ID. If we would have configured priority, the one with the bigger priority would have become the designated router. So with this designated router only, they will have full relationship. All will share everything only to DR. And the DR will share it to others so that there won't be a duplication. Yeah. So instead of everyone sharing everything to all, which may cause duplication and loop, we just share it with one person. All will select that one person as the, all will agree that one person as the leader of the gang, the DR router. And whenever they want to say something to others, they will not directly say, they will just go to this DR and say, and the DR will inform to others. By doing that, loop is prevented. Duplication of update is prevented. So if you are going to talk only to DR, there should be a special address, correct? This is the address. If anyone wants to send any information, they will send it to this address. Only DR can learn if you are sending to this address, .6. Any router that is elected as a DR will be responding to the address, will be owning this address. So all notifications are sent to DR using this address. And DR is now going to share that information to others by using .5, meaning if any packet is sent to .5, all other routers can receive it. Yeah. So there are two multicast address in this Ethernet environment, in this multi-point environment. Two multicast address, 6 and 5. 6 is the address used to send updates to DR. 5 is the address that will be used by DR in order to send update to others. Whereas in a point-to-point environment, you don't need the 6 because there is no DR. The only address that is used in point-to-point environment is 224.0.0.5. Any question?
So, small doubt.
Mm-hmm.
Why it is using a common multicast address to share that I am the DR?
I'm not getting you. Can you repeat, please?
So why the multicast address is used to share this? So I was under impression multicast addresses will be generated only if any of the devices want to join a multicast group and get a streams. So this logic I'm not getting.
See, this is also the same logic. What you understood about multicast is the same thing here also works. I'll tell you how. You see, whenever I say 12th standard, the 12th standard is a group of children in a school. To identify that group, I have 12th standard. Likewise, teachers. When I say teachers, that is also another group in that school. So, as a principal of the school, in the assembly, in the common assembly, where every classes are gathered, I want to address something to a particular group. DR is also a group. Here, it is a single router. But when you include backup designated router, that is also a DR. Only the difference is when DR receives an update, it will send to all other members, which means that is another group, other or another group. DR and BDR is one group. Difference between DR and BDR is this is only for backup. It won't talk. It will collect all the information that is coming. But DR not only collects the information when an update comes, it will also forward that information using this multicast address to another group called other groups, other routers. They are another group. So, in order to identify DR, you have this. See, they have their own IP address, but currently this is DR. Later, there may be another router as a DR. This backup router may become a DR. So, because the DR may change, you cannot identify it with one point-to-point address, with unicast address. It should be identified with a multicast address, because they will not be. The DR is not permanent on one router. If that router goes down, there will be another router elected as a DR dynamically. You are not going to configure anything. So when another router becomes DR, that will own this multicast address. That's why we use multicast address here. See, two reasons I have told you why we need to have this multicast address. Whenever there is a change, I need to send the update to DR. And DR is not one router, there is also one backup router. So it is again a group only. More than one is always a group. Always called as a group. Secondly, the reason why we need multicast address, the reason is I cannot use a point-to-point address because every time a DR goes down, there will be another DR, some other router which we really do not know now, will get elected. So to identify that router, you don't need an IP address. You can use that same 224.0.0.6. When a DR changes, you don't need to worry about what address to send. It's the same address you're going to send. And whichever the router that is the DR now will respond to you. Did I answer your question?
Yes, sir.
All right. So next is the sequence number. In the previous chapter, we saw when a packet is received, the sequence number is compared. When the sequence number that we have in the update is lower, then the incoming update will be added to our database. The old will be removed. Now the sequence number begins with this. Every time a change happens, one get incremented. It's a 32-bit size. It's a 32-bit size. You see, these are all represented in hexa. Each bit is 4-bit. Each hexa bit is 4 binary bit. So I have 1, 2, 3, 4, 5, 6, 7, 8. 8 multiplied by 4. 32. Okay. So this is the very first packet, very first sequence number. When these all zeros become F, instead of switching it to 9, it will switch to this one, so that it can again start from 8, isn't it? If you reset to 7, FFFFF, which means the last of the 7, the very immediate next one is 80000. And the very first update will be 1, 800001. So this is how the reset happens. This is how the sequence number. So we have 32-bit for the sequence number. So whenever change happens, only one is going to be incremented. With 32-bit, you can have around many million, I tell you. Many million updates can be, changes can be in the network. For each changes, there will be one number incremented in the sequence number field in the update. Now, what if this, now I told you many million, but still, it will not run out because every 1 hour, whether any change happens or not, the sequence number will be wrapped around to this. We'll get resetted to this number again from the beginning. So you will not run out of sequence number. Next. In order to make sure everyone is fully synchronized, every 30 minutes, the complete DBD will be shared in order to make sure that everyone is in sync. Here in this example, what you see is this particular advertisement advertised with this router has just come 48 seconds ago. That was the 8th update, 8th change about the network, 8th update. Likewise about this, 6th update was received like 212 seconds ago. This I already showed you, capture by debugging. Right, so this chapter is about packet types. What is packet type number 4? Anyone?
Is it the acknowledgement type?
No. Type 4 is LSU.
Okay.
LS update. Type 5 is acknowledgement. See? Type 4 is LSU. Type 5 is acknowledgement. All right.